properties of infinite series. So you can see here the necessary condition for convergence, and that is as indicated. Now, luckily, I had a backup copy of this, but actually, this was a copy. I thought I had more. Well, there we go. That will do it. That's where the chart went to. But the necessary convergence property was, well, essentially, if the series converges, then that limit is equal to 0. So if the limit is not 0, then that means that automatically you know that it diverges. All right, so hopefully that makes sense what is going on here. So it doesn't say that, you see how it doesn't say that if the limit is 0, then it automatically does converge. It just says that if it converges, then the limit is 0. All right, so then the sufficient condition for convergence, if the limit as n goes to infinity of an does not exist, or if the limit exists but is different from 0, then the series is divergent. So tell whether each series converges or diverges. So the first one here, so what we're going to do is we're going to start by figuring out whether the limit is equal to 0 or not. So this is AK, so AN would be for this, the series here, e to the n over 3e to the n plus 7. So we're going to find the limit as n goes to infinity of an. So that's the limit as n goes to infinity of e to the n over 3e to the n plus 7. So this, if I try to find that limit, that's an indeterminate form of infinity over infinity. So that means I can use L'Hopital's rule here. So then now, by the way, I again probably should think of this as a function and go ahead and use x's here, but I am going to assume that you would be able to do that off to the side on your own, given that I, again, never gave you a property for L'Hopital's rule for limits of these sequences. All right, so keep that in mind also. So now the derivative of e to the n, derivative of 3e to the n plus 7, 3e to the n. The e to the n's divide out, so I have 1 over 3. So since the limit exists but is not 0, that means that the series diverges. So again, like right away, if the limit is not 0, then you can tell right away that the series diverges. So let's try another one here. So here is AK, so AN is n over cosine of n. So we're going to find the limit as n approaches infinity of n over cosine of n. Now, there's lots of ways to go about doing this, but one of these is to just say that because you know that this limit is actually infinity over, and the cosine kind of alternates between negative and 1 and 1. So negative 1 less than or equal to cosine of n less than or equal to 1. So this is like an upper bound on it. So I know that this limit is always less than or equal to limit as n goes to infinity of n over 1, which is equal to infinity. So therefore, since the limit is not 0, the series diverges. All right, so hopefully you enjoyed that. I don't think that that one, again, was too particularly difficult either. It's just the fact that you have to sort of make sure that you uh, know what technique for finding the limit to use at which time. All right, so now let's find the next page. The next one will be a little bit more difficult, probably. So, do you have any questions? Does anyone have any questions about that so far? Okay, so again, if you have a question, just ask. I'm not here for myself. Like if I were here for myself, like that would seem strange if I were talking to myself. So, linear property of series. Oh, wait, where is it? C. Sorry, I did not even see problem C. So sum k equals 1 to infinity of k factorial over 2 to the k. So we have the a to the, or ak was k factorial over 2 to the k. So an is n factorial over 2 to the n. So we want to find the limit as n goes to infinity of n factorial over 2 to the n. All right, so now I need to pretty much determine whether the numerator is actually getting bigger faster than the denominator, or is the denominator getting bigger faster than the numerator, because that will tell me whether this should be infinity or whether it will be 0. All right, so keep that in mind also. So in other words, what I'm saying here is that if n, and then we have n factorial, and we have 2 to the n, right? If n is 1, n factorial 1, 2 to the 1 is 2. If n is 2, 2 factorial is 2, 2 to the 2 is 4, and then we have 3, 6, and 8, 4, 24, 16, 5, 120, 32, and 6, 720, 64, 7, 5040, 128. So I'm talking about the order of the numerator and the denominator. So the I'll write over here. So the numerator, you see what is going on here? Like at some point, the numerator was actually smaller than the denominator, right? And then by the time we get to n equal 4, the numerator had already overtaken the denominator. All right, so the numerator, I guess Maxwell didn't like that and he decided to leave. That's kind of strange. I didn't know that that would be so upsetting, but the numerator is growing at a faster rate than the denominator. So another way to say that is that the order of n factorial is greater than the order of 2 to the n, or O of n factorial is greater than O of 2 to the n. So um, if you haven't seen the O notation, that's usually left for computer scientists and things like that, or they would talk about in discrete math if you're taking that, which I kind of would think that, you know, if you're interested in this type of thing at all, that you want to take a discrete math class at some point to get a little bit more of this type of thing. So this ends up being then infinity, the limit. All right, so therefore, since the limit is not 0, the series diverges. What a time to be alive, right? All right, so now let's move on to the linear property of series. So if actually you can see all these here, like it's I don't know if I really want to read them because they're sort of a little bit wordy to read, and if like I read them, I'm really not sure how much it would help, but I will point out the couple of things that are important. That the two series have to be convergent series. So if you have a series A and a series B, if these are convergent series, then the series A plus B and A minus B are also convergent. All right, so if the series A converges and the series B diverges, then the series A plus B diverges. And if A is a convergent series and C is a constant, then CA is also convergent, and you can bring that constant C in front of the series by the homogeneous property for the sums here. And if A is a divergent series and C is a non-zero constant, then the series CA is also divergent. So D, we have what probably looks like it is, well, Maxwell is back. All right. So looks like it's a possible mess, but what I'm going to do here is just look at these two terms separately. So here is AK and minus BK. So we have sum k equals 1 to infinity of a half to the k minus 1 minus the sum k equals 1 to infinity of negative 1/3 to the k plus 1. Now, I already can tell, hopefully, that this is geometric because the exponent here on the base here is to the k minus 1. So this is geometric, and then the a is equal to 1, the r is a half. So since the absolute value of r was less than 1, this converges to a over 1 minus r, or 1 over 1 minus a half, so 1 over a half, which is 2. So that term converges to 2. Now I look at the other part here. All right, so if I look at the other part here, this has an exponent to the k plus 1 power. So I need to pull out a term to make it to the negative 1, right? K minus 1 power. So one way to do this would be to, now there's definitely a lot of ways to do this, but one way would be to perhaps rewrite it so that it's negative 1/3 to the uh well, all right, now um I actually want to make sure that everyone is clear on this, but all right, so if I want this to be to the k minus 1 power, but I want the exponent to remain k plus 1. This is like x, right? So k plus 1 is equal to x plus k minus 1. So then the k's actually zero out. Then you add the 1 to get 2 is x. So this should be 2. All right. So this is minus the sum k equals 1 to infinity of negative a half, sorry, negative a third to the second power times negative a third to the k minus 1. And now this is geometric with a is equal to negative 1/3 squared, or 1/9, and r is negative 1/3. So since the absolute value of r is less than 1, this converges to the a over 1 minus r, so 1/9 over 1 minus negative 1/3. So that ends up being, well, oh boy, 20, is it like, no, 1, it should be like 20, wait, no, so 1 over 9 over 1 plus a third. I think I'm doing the mental math wrong. 1/9, so that would be 1/9 over 4/3. So that would be 1/9 times 3/4. So that's 3/36, which is, yeah, so 36, not 20 something. So 1/12. All right. So now the original series then. All right, remember we had the 2 minus the 1/12, so 2 minus a 12th, that will be 24 over 12 minus 1 over 12, so that would be 23 over 12. What a time to be alive. All right, so this is why I talked about the geometric series first, because we sort of needed those to do this type of problem here. So if you don't have any questions, I'll move on, but I will give you a second to at least ponder this. Maxwell, I'm glad that you made it back. So, our So the sum k equals 0 to infinity of 2 times 1/3 to the k minus 3 times negative 1/5 to the k plus 1. So the one thing that you should notice here is that this is the first problem we had where k is not starting at 1. All right, so please keep that in mind, because that sometimes will throw people off, especially if you're not paying attention for it. All right. So I want to get this to start at 1 and not at 0. So if I look at this, then I can pull out the 0 term. So if you think about this, like if I wrote this all out, I normally write this out long form as 2 times 1/3 to the 0 minus 3 times a negative a fifth to the 0 plus 1, then plus. Instead of writing out all the rest of the terms, I can just leave it as sum k equals 1 to infinity of 2 times a third to the k minus 3 times a negative a fifth to the k plus 1. All right, and then I'll figure out what these first two terms were. So 2 times a third to 0 is 2 times 1 minus 3 times negative fifth to the 0 plus 1. That's negative a fifth. So we know we have 2 plus 3/5 no matter what. So keep that in mind that no matter what, we have 2 plus 3/5. And then I'll go ahead and I'll use the linearity property of series to write this as sum k equals 1 to infinity of 2 times a third to the k, and then minus 3 times, I'll bring out the negative 3, k equals 1 to infinity, negative 1/5 to the k plus 1. And actually, if I wanted to, like I could have similarly brought out the 2 here, made it plus 2. All right, so now I am going to use the same sort of tricks that I used before to rewrite this as a geometric series and rewrite this as a geometric series. All right, so I can rewrite this as 2 sum equals k, or k equals 1 to infinity of 1/3 to the, well, that would be the first power times 1/3 to the k minus 1 power. So 1 plus k minus 1 still gives me the k power minus 3. Sum k equals 1 to infinity of negative 1/5. And this will be to the second power times negative 1/5 to the k plus 1 power. And so, oh, sorry, k minus 1 power. There we go. That k minus 1 power. So then I can check 2 plus k minus 1 is still k plus 1. All right, so now this is geometric with a is a third and r is a third, and this is geometric with the a is, well, if I square the negative 1/5, 1/25, and r is negative 1/5. So here, the absolute value of r is less than 1. So the sum is the a over 1 minus r. So 1/3 over 1 minus 1/3. So that ends up being, well, 1/3 over 2/3, so a half. And then the next one, absolute value of r is less than 1. So this ends up being a over 1 minus r. So 1/25 over 1 minus a negative 1/5. So that will be 1/25 over, oof, that's actually, honestly, that's quite a lot here, but that would be 1 plus a fifth. So that will be 1/25 over 6/5. So that's 1/25 times 5/6. So then if I go ahead and I divide that out, that ends up being, I divide out the 5, so I have 1 over 5 times 6, so 1 over 30. So then if I combine all of this together, remember I had the 2 plus the 3/5 plus the 2 times, so 2 times a half, and then the minus 3 times the 1/30th, so 2 times a half minus 3 times a 30th. So we have 2 plus 3/5 plus 1 minus 1/10. Oh, what a time to be alive here. So then 2 plus 1 is 3 plus 3/5. So I'll make a common denominator with the 10. So 6/10 minus 1/10. So that's 3 plus 5/10. So that's just 3.5 or 7/2. So this ends up being 7/2. All right, what a time to be alive. So again, all I did was pull out the zero term and then use simple geometric series to do these. So if you have any questions, let me know. But I think again, the fact of the matter is that I really think the hardest part is just recognizing what to do when, because of course this is all self-contained, that we're only looking at like this type of problem right now. But that is also why I said that the flow chart would be a good idea to have, because then you know, like if the limit is equal to 0, then you need to try something else, like what some of the techniques we've been doing. Otherwise, the series would diverge automatically. All right, so just keep that in mind, that the checklist will help you if you get stuck on where you should even start. But here is another great example today. It's the sum k equals 1 to infinity of sine of 1 over k plus 2 to the negative k plus, minus sine of 1 over k plus 1. So if I rearrange the terms a little bit here, all right, just a little bit, then I will write these two terms together so that it's sum k equals 1 to infinity of sine of 1 over k minus sine of 1 over k plus 1 plus 2 to the negative k. And why am I doing this? Because this here is a telescoping series. So this will be telescoping, and then this part I can write as 1 over 2 to the k, which means that I'm going to end up writing it as a geometric series. All right, so how would I know, like, this is telescoping? Well, remember that the sum k equals 1 to so just the sum equals, and I just want to make sure that I want to say one other thing, but like if in either case I will just say this here then before I said anything. But I got the letters correct because I was going to just repeat A and B, but that's okay. We'll just repeat A. So AK minus AK plus 1 is a telescoping series. All right, so just keep that in mind as we go here. So now let's write out the terms so that we know what we have for the telescoping series, because this is a telescoping series, so it converges. All right, so right, yeah. All right, well, as long as this sum of the limit of the partial sums is finite, then it converges. All right, but we're going to, so it again means that we should look at these terms. So it looks like if k is 1, we have sine of 1 over 1 minus sine of 1 over 1 plus 1. Then if k is 2, I have plus sine of 1 over 2 minus sine of 1 over 3. Then if k is 3, I have sine of 1 over 3 minus sine of 1 over 4, and then so on. And then I'm left with a sine of 1 over, all right, 1 over n, all right, minus sine of 1 over n plus 1. All right, keep that in mind of what I'm actually doing here. All right, and then you'll see that all of the terms will cancel out except for the first and the last one, because there's sine of a half canceling out, sine of a third canceling out or zeroing out, and then sine of 1 over n would zero out with this term right here. So I'm left with sine of 1 minus sine of 1 over n plus 1. So if I want the limit as n goes to infinity of sine of 1 minus sine of 1 over n plus 1, then as n goes to infinity, this would be actually like essentially 1 over n plus 1 is going to 0. So this ends up being sine of 0, which is 1. All right, so that's sine of 1 minus sine of 0. So that's sine of, did I say 1? No. Yeah, no. Wait a second. Yeah, 1 over this large number, which is 0. So it's sine of 1. All right, there we go. So now that means, what do we need to do? We just really need to figure out what this part is doing. So we have sum k equal 1 to infinity of 1 over 2 to the k, so that's 1 half to the k. So I'll rewrite it as 1 half to the 1 times 1 half to the k minus 1. So now this is geometric, and that's geometric with the a is equal to a half and r is equal to a half, and then since the absolute value of r is less than a half, this converges to the a over 1 minus r, so a half over 1 minus a half, which is 1. So the whole series ends up being, I'll just write it over here, but it's sine of 1 plus 1. All right, sine of 1 plus 1. All right, so before we move on, does anyone have any questions about that? Because we only have 3 more examples here, and this will just be, again, just some more examples of like removing terms and then just seeing how you could approach the series from there. And the only 3 approaches, again, that I've really had were rewriting as a geometric series, or looking at something where I'm putting a bound on it, like I did with the cosine of n, or looking at a telescoping series. So those are actually the only 3 things that I've used in terms of techniques so far. So just remember that also. But this one was a little bit all over, possibly, but hopefully you enjoyed that. And now let's look at this, and you can again read these here if you would like. This is what I was doing when I removed the 0 term for the one problem earlier, and this is sort of describing what I was talking about when I was talking about upper bound for the uh, the series by putting the bound on that cosine earlier. So now here is an example. We have the sum k equals 1 to infinity of k minus 1 natural log of 3 over 4 to the k minus 1. So this might seem like it's actually a little bit harder than it actually looks, but all I'm going to do is I'm going to start out by using the power rule for logarithms. Right now, if you think about this, up until now, we wanted to get the exponent out of the power by using logarithmic differentiation or something like that. But in this particular case, we're actually going to put the k minus 1 back into the exponent, all right? So this will be now I'm going to just look at the partial sums now, just so that you're aware of this. All right, so we're going to look at the partial sums. So Sn, the partial sums, will be sum k equals 1 to n of natural log of 3 to the k minus 1 over 4 to the k minus 1. And now I am going to look at this and see if I can rewrite that to compare it to some other series. Well, a series that looks similar to this would be, well, sum k equals 1 to, n, all right, just n, of 3 to the k minus 1 over 4 to the k minus 1. All right? So now I need to know how this would compare, and what I really want is for this to be, again, an upper bound of some sort. So I want to make sure that whatever I get here is going to be bigger than what I get here. So if you think about it, it is, because natural log of 3 to the k minus 1 is that smaller than 3 to the k minus 1. Like, is that smaller? Well, if I take the logarithm of a number, I get a smaller number, and indeed. All right, so keep that in mind also. Or you could go ahead and do some weird stuff here to figure this out, but I'm not I'm not sure that you would want to do that. I would just verify it by graphing. If I had my calculator, I would show you. Here we go. So, oh no, I don't actually know what is going on here. So, okay, so natural log of 3 to the x minus 1, and then we have 3 to the power of x minus 1, and then if I graph these, oh no, what is going on here? I have no idea what is going on here. So, oh boy, zoom, standard, it didn't do anything. Zoom, there we go. So there is the log, and there should be the graph of the exponential function. So you see at every point here, the exponential function always had the larger value, all right? So that means that this is definitely true. So that's less than this. But then I can say this is less than or equal to the sum k equals 1 to infinity of 3 to the k minus 1 over 4 to the k minus 1. And I know that this is actually less than or equal to this because this has n terms and this is going to infinity. So this one with more terms in it will have a larger sum than the sum with fewer terms. All right, but I needed this to go to infinity in order for me to use the properties of a geometric series here. So now I'm going to rewrite this. This is actually equal to, all right, equal to the sum k equals 1 to infinity of 3/4 to the k minus 1. So I'll just rewrite this, and that means that a is 1, r is 3/4, so this is definitely geometric. All right, so then that means this converges, since the absolute value of r was less than 1, this converges to the a over 1 minus r, so 1 over 1 minus 3/4, so 1 over 1/4, which is 4. So this means that this actually will end up being equal to something that has an upper bound of 4. So that means Sn is bounded above by 4. So therefore, the series that we were originally dealing with, k equals 1 to infinity of k minus 1 natural log of 3 over 4 to the k minus 1 converges. But again, that doesn't mean that it necessarily converges to 4, but all we found out is that it does converge. All right, so if I take the liberty of telling you like what it converges to, let me calculate this value for you real quickly. So let's see. Well, yeah, because this is actually very interesting, because I don't want you to get trapped in that sentiment that this is actually what it converges to. But so, but not to 4, because the exact sum is actually, well, how many digits do you want to see? It's 0.48827 to 8, so on, but it really is uh, 3 to the, what is 3 to the 4th power? I don't know. 3 to the 4th power is, yeah, so so natural log of 81 over 9. All right, so natural log of 81 over 9. Yeah. So if you wanted to know the exact value, then you could find the exact value at some point in your life if you really cared that much about it. But all I asked for was, did this series converge or not? All right, so just keep that in mind, that I am not going to actually have you find that exact value, unless, except for Maxwell. I mean, you can always find that every day, but I'm sure that you already knew it just by looking at it. All right, so now let's look at another example here. So there's 2 more here and then we'll be done, but this one is a little bit different here. K over 5 to the k. So, oh, by the way, this is, oh, oh boy, yeah, so I'm looking at something else. All right, so let's look at the partial sums again. So sum k equals 1 to n of k over 5 to the k. So another way to write this would be sum k equals 1 to n of k times 1 over 5 to the k, or sum k equals 1 to n of k times 1 over 5 to the k. I'll tell you, I'm kind of glad that this is the last page because I'm getting really hungry. I got up earlier this morning and I had 2 Pop-Tarts, and the store really didn't have very much of a selection left, so I got some new ones that were the pretzel ones. And if you haven't tried the pretzel Pop-Tarts yet, I wouldn't recommend it because they taste sort of a little bit like they're the normal Pop-Tart on the back, but they taste really like too chewy on the front. Although it's more like a soft pretzel with like feeling and not like how I envisioned it would be, you know. So it really didn't go well with the Pop Tart, but I thought it would be a harder pretzel, more like if you get a pretzel combo, like the like pizza filled, that's usually the best kind, or the cheddar ones with the pretzel. But anyway, I will say definitely lunchtime soon. So now I can rewrite this part here in geometric form. So sum k equals 1 to n of k times 1/5 times 1/5 to the k minus 1. But this part right here, this k in front, means that this is still not in geometric form. All right, so I know that k is less than or equal to 4 to the k minus 1. If you didn't know that, now you do. All right, so just add that to the list of things to memorize for the rest of your life, and then you'll be fine. So this will be less than or equal to sum k equals 1 to n of 4 to the k minus 1 times 1/5 times 1/5 to the k minus 1. And then if I combine this here, 4 to the k minus 1 times 1/5 to the k minus 1, that will be 4/5 to the k minus 1. So this is equal to sum k equals 1 to n of the 1/5 times 4/5 to the k minus 1. So this is geometric with the a is equal to a half and r is equal to 4/5, but since the absolute value of r is less than 1, this means that this converges. So converges with well, sum equal to a over 1 minus r, so 1/5 over 1 minus 1/5, so that will be 1. So that means that this is bounded above by 1. So this is equal to 1, so therefore Sn is bounded above by a finite number of 1, so therefore the original series, sum k equals 0 to infinity of k over 5 to k, converges. And remember, all I said was that I asked whether this converged or diverged, but not to which value. So there we go, that converges. If you want to know the exact value that it converges to, it happens to be 5 over 16. But again, we won't calculate those except for Maxwell, all right? So I'll just ask whether this needs to, or whether it converges or diverges. All right, last one here. So if you have any questions, again, feel free to ask, but I'll look at the partial sums for this series here. So Sn is going to be sum k equals 1 to n of 1 over k factorial, but I am going to say that this happens to be less than or equal to sum k equals 1 to n of 1/2 k to the, 1/2 to k minus 1. Now, if you think about this, this sort of makes sense because if you remember the one example that we did earlier, remember this example here where I said that the order of n factorial was bigger than the order of 2 to the n. So I know that the uh, since the order of n factorial is greater than the order of 2 to the n, that means that if I take the reciprocal, then I know that this is where, in a similar fashion, this is how I'm getting that. All right. So just keep that in mind that this isn't a series, like I said, that I haven't showed you already. You've seen this already. I'm just asking it in a different way. Like we had the basic geometric, the telescoping, this upper bound one. All right, so those are mainly it. So now this is definitely geometric, and that's geometric with the a is equal to 1 and r is 1/2. So this converges to. Now remember that since the absolute value of r was less than 1, this converges to a over 1 minus r, or 1 over 1 minus 1/2, so that will be 2. All right, so that means that Sn is bounded above by 2, so therefore the series k equals 1 to infinity of 1 over k factorial converges. And if you want to know what it converges to, and again, only Maxwell has to calculate this, but it converges to e minus 1. So that's all I have the on the section here. So that would be the properties of infinite series.